Hey folks, so I'm just going to start going over some of these little short quizzes you've had at the end of each day. What happened to, oh, there we are. So this first one, finding frequency and period from graphs. Now, before I even go over any of the specific questions, I should really mention that if you have some kind of graph, some kind of simple harmonic motion, that really just means it kind of repeats. It doesn't matter if it's like kind of this way, we would have a positive cosine, or if it's this way, we'd have a positive sine, or maybe it's this way, this would be a negative sine, or maybe it's this way, this would be a negative cosine. So it really doesn't matter which one, but we have something that just repeats over and over and over, and we can kind of see by this kind of repetitive motion. And so the first idea here is that the period, given the symbol t, I know it's a little weird, but maybe it's kind of like time is little t, so period's big T. It's a time for it to repeat. So it doesn't matter if it's at the kind of maximum amplitude, that would be the maximum amplitude. Then this would be from here to here, that would be a period. Or it could be, well, from equilibrium and going downhill to equilibrium and going downhill again. So this would be our period as well. And if I did a really good job drawing it, this length would be the same as this length, because this axis really would be time, and this axis really would be kind of our displacement, our x position, and that would be kind of as a function of time. So it really doesn't matter. It's from one point to the next matching point. So it's until it repeats again. That's period. Now, frequency, though, little f, is actually the reciprocal of period. It's 1 over the period. So that means that if the period was, I don't know, 2 seconds, that means it takes 2 seconds for a wave to fully repeat, or this kind of oscillator to repeat its motion. I don't mean to say wave, it just looks like a wave. But if it has a period of 2 seconds, well, that means that it takes 2 seconds to do a full repetition. Well, that means then that the frequency here would be 1 over 2 seconds, which is really 0.5, and the units for 1 over seconds is hertz. I know all these units hurt to learn, but all that means is that, well, it does half of a wave in 1 second. So the frequency is half a wave per second, so 0.5 hertz. And that totally checks out, because if we're doing half a wave in 1 second, it does take 2 seconds for one repetition. So it actually kind of checks out on its own there. So let's look at the questions themselves now. So first one, we have this graph. What is the frequency? That's it. That's all it's asking. So I could pick any 2 points. I just like to pick the first one and then find what repeats again. But if you wanted to be kind of awkward and painful about it, you could pick any position. So let's just pick right here. Well, we're at our maximum negative amplitude. And so maximum negative amplitude again. So that means that our period t would be 2 seconds. And oh, whoa. Well, if the period is 2 seconds, this is the example I just did above. Frequency is 1 over the period. So that gives us 1 over 2 seconds, which is the same as 1 over 2 hertz, or 0.5 hertz. So there we go. All right, let's look at the next one. Student has some mass and it's attached to a spring. We're given this graph, and what's the period? That's what they're really asking us for here. What is the period? Now, one thing I want to mention is in the previous graph, this was kind of centered on our x-axis. It was kind of symmetric, so we have the same amount of stuff above as below. This graph is just trying to make you a little more comfortable with the fact that it doesn't have to be shifted up here. So maybe instead of having our starting point at 0 here, our starting point is at 4 here. So that's it. It's just kind of shifted. But what's the period? It's the same thing we've already been talking about. So maybe I pick right here, and we're at equilibrium and going up. So I don't want to pick here because I'm at equilibrium and going down now. So that's a no-no. But let's go right here. And if we check from this, well, we start at 0 seconds. We're going to 4. So we have a period of 4 seconds for it. Cool. A student extends some mass attached to a spring. A graph of its displacement over time is shown. What's the frequency? Oh, so this is kind of like that first question we had, but it's actually the graph we just looked at before. So if I'm looking here, well, we already know from before the period here is 4 seconds. Well, if frequency is 1 over the period, well, we're going to get 1 over 4. 1 over 4, that's the same as 0.25 hertz, or 1/4 hertz. Boom. Okay, same setup, graph of displacement over time. What is the period? Hopefully we're kind of getting a groove on this now a little bit. Well, the period, again, we know period is just matching points. So let's just make things a little interesting. Maybe I pick like right here. I'm at 1 second. I'm kind of like, I don't know, a little over halfway down to this like kind of crest down here, this bottom part. Well, I would have to go over, and since this is all nice and symmetric, I could go the same position on the following wave. And since I happen to line this up with 1 second, and this is with 4 seconds, well, 1 second to 4 seconds, the time elapsed there is actually only 3 seconds. And if I chose this point and I went from here to here, we would find that they actually are the same distance, because we're going from 0 seconds here to 3 seconds here. So our period is 3. Our frequency, though, would be 1/3 hertz. And that's it. Cool. Bye for now.